Hello and welcome to lecture number 18 in the course Advanced Robotics. In the last class, we looked at the general definition of sensors and actuators, and I also explained the very basic closed-loop control system. What are the various elements that are involved? For example, there is a controller, then there is an actuator, then we have the robot or the link, and in the feedback loop, we have the sensor. And connecting all of this in a closed-loop control system, we have a closed-loop control system. So in the last class, we talked about sensors. So we'll continue our discussion on sensors. And then today we'll start talking about actuators. Okay, in the last class, we were talking about sensors and actuators. And we gave the very general definition of sensors and actuators. I explained also the various subsystems which are involved in the control system, in the closed loop control system. So we have a controller, which can be a PC, it can be a microcontroller or a DSP. Then we have an actuator. In this case, it's a motor. And then we have the link of the robot, which is actually moving. And in the feedback loop, we have an optical sensor, which is a sensor to sense the position, or a position sensor. And this makes up my closed loop control system. I also explained that how this closed loop control system works and what is the requirement for an actuator and a sensor here. Now, the four basic elements which make up the control system consists of sensors, actuators, controllers, and a system model. And all of this is connected in a closed loop control system. Now, when we're talking about the basic definition, so we said the basic definition of sensors and actuators are that they convert energy from one form to another. And I gave the example that in this particular case, in this motor, the controller gives a voltage as input to the motor, a voltage signal, or rather it gives a voltage signal to the motor, and which is a voltage to the motor rotates, so there is conversion of electrical. So here it is electrical energy to mechanical energy conversion. So in an electric motor, we have conversion of electrical energy to mechanical energy, and when it is converted to mechanical energy, the link moves, and when the link moves, the position of the link is sensed by the sensor, and there is a feedback, and the sensor again converts mechanical energy to electrical energy, and this electrical energy is fed to the controller. Now the controller is essentially an electrical device, whether it's a microcontroller or it's a PC, or it can be an FPGA or a DSP. It is essentially an electrical device, so it understands electrical signals only. So the output from the controller will be an electrical signal, and hence what you're giving as input to the controller also should be an electrical signal. And because the actuator is converting electrical signals to mechanical energy, so we have electrical voltage to mechanical rotation, what we need to do is we need to convert this mechanical rotation back into electrical energy again, and that is what the sensor is doing. So in this particular sense, in this particular closed loop control system, the energy conversion is going on from electrical to mechanical, and then mechanical to electrical again. Okay, so here it's an actuator and here it's a sensor. So in terms of definitions, sensor and actuator definition is the same. The energy converters from one form to another. In this case, it's electrical, but you can have other kinds of energy conversion. For example, from hydraulic energy to in a piston cylinder mechanism, hydraulic energy to mechanical energy. Okay, or you can have pneumatic energy to mechanical energy, or you can have steam to mechanical energy again. Okay, so it can be different kinds of energy conversion. In robotics, mainly we are dealing with electrical energy conversion from electrical to mechanical, and then mechanical to electrical. So this is the basic definition of a sensor and an actuator, and it consists of basic control elements are these four that make up the control system. Now we started off by discussing about sensors, and for sensors we say that sensors can be divided into internal sensors and external sensors. Internal sensors are required for the basic working of the system, for example, position, velocity, acceleration. So if I have a robot, we also talked about independent joint control, in which we said that every link of the robot, or rather every joint of the robot, is connected to one unit consisting of a motor, encoder at the back, and a gear in front. So each of the joints are connected to one unit of each of these actuator sensor units, and the controller assumes that each joint is not interacting with the other joint, and this is what we call by independent joint control. So here we said that for the basic working of this joint, what we need is an actuator and we we need a sensor. The sensor has to tell what is the present position of the joint or the links, right, to the controller, so that the controller can decide how much voltage or how much actuation to give to move the link from some position to some other position. For example, we are here and I want to move it to some other location like this. Okay, essentially it is saying theta 1 is moving from theta 1 to theta 1 dashed. Okay, if I say this is my theta 1 and that's my theta 1 dashed, so the controller must know what is the desired position and what is the present position. And once it knows that, it basically generates an error. So theta 1 dashed minus theta 1 is equal to del theta 1, and it drives this error to 0, which basically means that the difference between these joints are becoming 0, which means this joint is moving in this direction. And once they become the same angle, then the error becomes 0 and the controller understands that it has reached. Okay, so in terms of reaching the point, we basically drive this error to 0. Okay, so this error is driven to 0. So what we see here is that the controller must know at every instant what is the desired position and what is the present position of this, and this is given by the sensor. Okay, so there are internal sensors which are required for the basic working of the system, like position, velocity, acceleration, and without this the robot cannot function, and hence they are called internal sensors. External sensors are required for interaction with the environment. For example, if there is an obstacle here, I need some kind of sensor which is going to tell me what is the distance from the end effector to this obstacle, so that it can avoid the obstacle and go like that. Okay, so this is another kind of sensor, and these are for interaction with the environment and are called external sensors. So they can be vision, they can be distance, it can be force, it can be torque. Okay, so these are different kind of external sensors. In the last class, we started talking about internal sensors, where I covered the potentiometer, then the incremental encoder, and then we saw the absolute encoder, and also proximity sensor like the inductive sensor. So today we'll just briefly revise. So we are talking about proximity sensors, and proximity sensors are basically of different kinds. We can have inductive sensors. In proximity, as the name indicates, it means that how close you are to an object. That is the meaning of the word proximity, how close you are to an object. Okay, that gives us the distance from an object or the proximity of an object. And these are non-contact kind of sensors. So these are non-contact sensors. Okay, and the simplest example is this inductive sensor. So we have, and how this works is we have a magnet. So there is a magnet in there, so that there's a north and south pole there. And this is contained in a container, which is basically a cylinder which is made up of plastic. So what happens is this, because of this magnet, there will be magnetic lines of force which will be going like that. Okay, so these are the magnetic lines of force, which you can see in this figure. Now in this figure also it is seen that the magnetic lines of force are going like this, and in front of the magnetic lines of force there is this coil, and the magnetic lines of force do not cut the coil. Okay, so there is no EMF which is generated in the coil, because the magnetic lines of force are not cutting the coil. Now the moment an object comes in front, as seen in this figure here, the moment an object comes in front, what happens is that the magnetic lines of force are drawn out like that, and when the magnetic lines of force are drawn out, they basically pass through the coils, and then they are drawn out to that position, right? So when they are passing through the coil, what would happen? An EMF would be generated in there, so you get some voltage. Okay, so here the voltage is equal to 0, and here there is some volt, let's say 5 volts, just for example. Okay, so 5 volts can correspond to 1, and 0 volts can correspond to 0. So it basically means a 0 or a 1 signal. So the controller understands that when the signal is 1, means there is a voltage, it means that an object has come in front. Okay, and if it is 0, it means nothing has come in front. Now the advantage of this is that the working is very simple, there are no moving parts. But the disadvantage is that because it works on the magnetic lines of force, the object has to be steel or iron. It has to be ferromagnetic. Otherwise, the magnetic lines of force will not be induced and the sensor will not work. So this will not work for plastic and wood and things like that. But in the industry, as you know, a lot of the parts are made up of iron or steel. And hence, this is very good application. This sensor can be applied in industrial applications. For example, if there is a conveyor like this and parts are coming on a conveyor, okay, and there's a robot which has to go and pick it up. So when the part comes, a sensor has to tell the robot that the part has come. So this can be a proximity sensor which senses that a part has come. And the moment a part has come, it gives a signal of 1 to the robot. The robot now understands part has come. It goes there, picks it up, and takes it somewhere or does some other function. Okay, so this is a proximity sensor. The other types of proximity sensor which are very commonly used are Hall effect sensors. Now the Hall effect sensor essentially also senses magnetic lines of force. So this is a Hall effect sensor, and this is a horseshoe type of north-south magnet. Now the Hall effect sensor is placed inside, and the magnetic lines of force are passing like this. They are passing inside the Hall effect sensor. So you can see that the magnetic lines of force are passing through the Hall effect sensor. Okay. Now the moment something comes in front, in the second on the figure on the right, the moment something comes in front, what happens? The magnetic lines of force are drawn out. The moment they are drawn out, the magnetic lines of force are not passing through the Hall effect sensor. And if this is my signal of 0, then that's my signal of 1. Okay. Again, this has to be a ferromagnetic body, which will enable this Hall effect sensor to function. Okay. So how it functions? If a part comes in front, there's a magnet. So the magnet is going to induce magnetism into the ferromagnetic body, which is going to pull the lines of force out like this. Okay. And in pulling the lines of force out, the lines of force will not pass through the Hall effect sensor. And this is sensed by the Hall effect sensor, whether the magnetic lines of force are passing through the sensor or they're not passing through the sensor. And that is basically what it is sensing. Now again here, it works only for ferromagnetic material, but in industries, most of the parts are made of ferromagnetic material. And this is a sensor which is very commonly used. For example, in the cars, the speedometer, for example, how to measure the speed of a car. So if you look at the dashboard of a car, there are a lot of dials. One dial tells you the speed of the car. Speedometer gives speed of car. Okay, and there's another one that senses engine speed. So both these are displayed. So if you, for example, if you press the clutch and the car is not moving but the engine is running, then it will show you the engine speed, which is the engine speed. But if the clutch is engaged and the car is rotating, then it will give you the speedometer will show you what is the speed of the vehicle in kilometers per hour. Okay, and how is that sensed? So that is essentially sensed by using a Hall effect sensor, and the Hall effect sensor is fitted onto the crank of engine. Okay, and it senses the rotation of the crank. And number 2, so this gives you the engine speed. Okay, and it is also fitted on the gearbox. So in the gearbox, the output of the gearbox this is actually showing the output of the gearbox. So what is done is there is a projection on the gearbox output. Okay, and there is a Hall effect sensor. So when it is rotating, what is happening is, for example, if I just draw a gear here. So this is a gear which is rotating. So in this shaft, okay, there is a very small projection, okay, on the output shaft, and there is a Hall effect sensor which is sitting here like this. Okay, so this is exactly what is this one. So when this is rotating, if I take the side view, this is my side view, right? And this is my gearbox gear. So when this is rotating, every one rotation will go through and it will count one rotation. So it is like this part, this projection is coming in front of this once, and you get a voltage of V, of some volts, maybe 5 volts. So it gives a signal of 1, then it becomes 0, then it becomes 1, 0, 1, 0. So this is how fast this is rotating is basically being measured as the output of this is basically indicating the speed of the car. So in the car, a lot of the materials are ferromagnetic material, and hence this is used extensively in the gearbox and in the engine crank to measure the engine speed. So Hall effect sensors, these are extensively used not only in robotics but also in. Now when we talk about the DC motors, the brushless, what we call BLDC, I'll come to this subsequently. When we talk about brushless DC motors, they do not have brushes. So we need to sense the position of the armature. So armature position is to be sensed, and this armature position is sensed by putting 3. So this is my armature which is rotating in the motor. So when this is rotating, I need to sense the position for electronic commutation. So how this is sensed is by placing 3 Hall effect sensors in this star formation. So what happens is that when the poles are rotating, this is inducing magnetic field, and this is how fast it is rotating is being checked by this Hall effect sensors. So it is also giving you the motor speed. When we come to BLDC motors, I'll explain how this is done. Okay, the other So we have looked at proximity sensor, we have looked at Hall effect sensor. Now let's look at ultrasonic sensor. Now the ultrasonic sensors working principle is something like this. Now you know that ultrasonic, you know that there is a piezo crystal. Okay, piezo crystal. Now in the piezo crystal, if you apply a pressure, if I apply a pressure here, it will produce a charge. Okay, and if I give it a charge, it will produce a pressure. It will expand a little bit. Now piezo crystals or quartz crystals are also used in watches. Okay, so this, every time you give it a charge, what happens? It vibrates once. So that is how the second hand of the watch moves. Okay, in this watches which are actuated by quartz crystals. Now these are piezo materials. So if you give it a pressure, a charge is produced. If you give it a charge, a pressure is produced, a vibration basically. Okay, so this is a ceramic transducer or a piezo. Okay, and we give it a charge in a particular frequency. So this is the charge that is being given. So it is being given a charge in a particular frequency. Okay, so corresponding to this frequency, it is going to vibrate. Means it will slightly expand. Now if it vibrates at that frequency, in front of this crystal there is resin. So what happens? This vibrates also. Now if this vibrates, then ultrasonic wave is produced, a sound wave basically. Okay, so this sound wave goes out. If there is an obstacle, it hits the obstacle and then it comes back again. Now when it comes back, it hits the crystal again. So it is like a pressure wave which is falling on the crystal, and as a result of it, a charge is produced. Okay, so here is the signal that is going in. This crystal is being actuated, or rather the charge is being given at this particular frequency. A wave is being produced. This wave is going out. This is the driving signal wave. The wave is going out, it is hitting an object and coming back. Now if it comes back, you are sensing that the wave, once it hits the crystal, you are going to generate a charge. So this is a small charge which is being generated. So again, a wave goes out, it hits something, comes back, a small charge is generated. Now if you know the time interval between this and this, and you know the velocity of sound in air, then we know what is the distance of the object that it has hit and has come back. So this is a very simple sensor which is called an ultrasonic sensor, which is very commonly used in robotics, especially in mobile robotics. So in mobile robotics, this is very, very commonly used, where we have a mobile robot which is going around and there are obstacles. Okay, so it has to avoid these obstacles and go somewhere. So let's say this is a mobile robot with two wheels, differential drive. Okay, two wheels which are driven, and so it goes towards the obstacle. There would be ultrasonic sensors. Okay, so these ultrasonic sensors would sense how far, what is the distance of this object, and it will hit that object and it will come back. Sorry, it will not hit, it will just sense. So it gives the distance of d1, d2 from the obstacle, and if it is too near, then the robot can change its path and go in some other direction. Okay, so this is used for obstacle avoidance. Now again, this ultrasonic sensor is very cheap. Okay, now I forgot to mention something about the Hall effect sensors also. These sensors are very, very cheap. They're about 150 200 rupees, so they are extensively used. The advantage of a Hall effect sensor is that it's a solid state device, so it's a solid. Okay, there is no moving part inside there, because of which functioning of this requires very less charge. It is a very rugged sensor, and it can be placed in the car body, in the gearbox, in front of the engine. Okay, and this has no moving parts, so it doesn't get bad. Now similarly, this ultrasonic sensor is very cheap. It's about 200 rupees only, and you can actuate this by using a very simple microcontroller and use it on a mobile robot to get distance from an object. Okay, the disadvantage of this is that very often it does not see. Okay, why it will not see? For example, if an obstacle is there which is at an inclination, so if it's at an inclination, what will happen? It will hit this and it will go somewhere else. Okay, so the ray will not come back. If the ray doesn't come back, it will not see. So number one is shape of obstacle. Number two is if the rays are absorbed. If the rays are absorbed by the material. For example, if you have cloth, if you have wood, then what happens? These ultrasonic rays are absorbed. So if the ray doesn't come back, then obviously there is no signal. So it doesn't know that how far the object is. Okay. Now the other sensors are, so these are proximity sensors. The other kind of sensors are pressure sensors, which are used on fingertip of robots for sensing, for example, haptics. Haptics is one application of this kind of pressure sensors. How they work is very simple. So you have a row of electrodes as shown here. Okay, so there is one layer of rubber with rows of electrodes, and there is another one which has a cross row of electrodes. Okay, and in between there are this non-conductive rubber with holes. So if you press here, what will happen is this will go into the hole and contact this part. So what happens, it shorts. Now immediately it understands that the voltage is shorting there, so there will be a voltage across that. Okay, now if there is a voltage across that, it knows that connection has been made. Okay, or that is the point where you're touching. Similarly here, if you look at this particular case, okay, what is happening is there are this computing elements, or these are electrodes basically, and on top there is a pressure sensitive elastic material. So if I press here, what happens is this conductive material. So what will happen is this will short, this will connect with this computing element, or rather a conducting element, and then immediately connection is made, so it will give a signal of 1. That means voltage is going through. Now if voltage is not going through, it's 0. Okay, so this is how this kind of sensor works. Now in terms of pressure, this is a pressure sensor, and how this works essentially is you have pressure sensitive rubber on top, and you have a number of electrodes. Okay, here, 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 here. Now between the electrodes, you can see here that if there is no rubber, then what will happen, there will be no charge flowing through the electrodes because there is no contact. Now the moment you press here, what happens is, if you look at the figure below, suppose you put your finger and you press here, what happens is rubber gets into that, in between the electrodes now, and because it is conducting rubber, it will short these two electrodes now. So some voltage is going through. Now the moment voltage is going through, it understands that there is pressure being applied, and you can calibrate the force versus the voltage. So we can have force versus voltage and get some kind of a graph, and this graph will tell you how much force or pressure has been applied. Okay, so these are pressure sensors, touch sensors, pressure sensors, which are used in robot fingertips for touching, understanding whether touch has been made or how much pressure is being applied. They can also be applied on the sole of the foot of bipeds. So biped robots, we can apply the pressure sensors at the foot of the biped, so to understand when contact has been made, what is the center of pressure, what is the zero moment point when the robot is walking, and to maintain balance. Okay, so if you think about, when we're talking about pressure sensors, when you're walking, you're actually feeling the center of pressure on your foot, on the sole of your foot. So there are a lot of pressure sensors there. And when you're walking, so let's say this is walk, when you're walking, there are pressure sensors here at the sole of your foot, and this is how we ensure balance. So when you're walking, you can actually measure the center of pressure, and you can figure out where is the center of pressure and change your kinematics such that you don't fall down. Okay, when we come to gait planning, this is exactly what we'll see, how to do this by using pressure sensors. Now next we move on to force torque sensors, force and torque sensors. Now force and torque sensors are required by the robot to understand how much force is being applied. For example, if you're doing an assembly task, so you have an object like this, and you have a part which is given here. I want to insert this into this. So when we are inserting, there is a chance that this part will come in contact with this. So if it comes in contact with that, there is a force which is there, acting there. Okay, so if it gets jammed, for example, you would understand that you should not apply too much force, otherwise it will damage the robot or it might damage the part. So there is a requirement for measuring force. Now when you are screwing, for example, this is a screw and you're trying to apply a moment there to tighten the screw, then again the same thing, you should be able to measure the torque or the moment being applied, so that there is no damage on the robot, nor is there any damage on the part. Okay, so there is a requirement for measuring force and torques. Now we also need to measure torques in the joints of the robot. For example, we talked about, this is a robot which is, for example, applying a force of on the wall. Okay, so there is some force which is being applied, and this force is being felt at the joints and in the form of a torque. Right? For example, if a robot is moving in free space, this is an example you'll appreciate. Suppose a robot is moving in free space and suddenly it hits something. Okay, what will happen? An impact force will come. This force is going to get reflected onto the joint as a torque. So you should be able to measure that torque and if it has hit, it should immediately stop moving or it should go backwards, so it doesn't cause any more damage. So how is that done? That is essentially done by measuring the forces and torques which are acting on the system, okay, at the joints. So the question that comes up now is interesting question, that can you measure force or moment directly? Okay. Say for example, if I say that in this position, apply in air, apply 10 newtons in air. Can you do that? Okay, so I have a point in air, A, and I say apply 10 newtons there. Now, can you apply 10 newtons in air? You cannot. Why? Because there is no opposite and equal reaction. There is no opposite and equal reaction, so you cannot apply 10 newtons there. Whereas if I have a wall like this, and I say apply 10 newtons there, then you can apply 10 newtons there. Why? Because there is an opposite and equal reaction of 10 newtons. Now I can apply 10 newtons. Okay, but think about it in the other way. Suppose I say at this point A, move with a velocity of 1 meter per second at the point A in air. Okay, this is in air. Now can you move? Yes, you can move. So you cannot apply force, but you can move freely. In this particular case with the wall, I say apply 10 Newton here and move with 1 meter per second. Can you do that? Well, you cannot do that because there is an equal and opposite reaction and you cannot go through the wall. So you cannot apply a position, you cannot do any position control there. You can only do force control. Okay. So this is very important and interesting to understand that when can you apply a force and when can you apply a velocity? Can you do both of them in the same direction? No, you cannot do. Force and velocity cannot be applied in the same direction. So force and velocity cannot be controlled in same direction. Okay, that means on a wall, for example, if I press, I can apply a force, but I cannot control a velocity in that direction, in the same direction. Okay. Whereas in air, I cannot apply a force, but I can control a velocity in air. I can move my hand with 1 meter per second in free air, but I cannot apply a force. So the only condition under which a force and position can be controlled simultaneously if both of them are normal to each other. So I can say 10 Newton this side and I can say 1 meter per second this side. So when you're cleaning the wall, for example, or when you're writing on the wall, even when you're writing on paper, you're applying a force on the paper and you're moving in a direction which is perpendicular to that force. Okay, only under that condition it's possible. That means in the force space and the velocity space, they are orthogonal to each other. Please think about this because this is very, very important and very important to understand. Now let's look at, so if you cannot measure force directly, okay, you can measure force indirectly. What do you mean by that? If I say measure how much force is being applied on the wall here, there is no way by which you can measure it because you cannot measure force directly. So first of all, force and velocity cannot be controlled in the same direction. The next, force and moment cannot be measured directly. What is the meaning of this? The meaning of this is that you cannot measure force directly. You can measure the effect of force. So what we are doing is we are measuring the effect of force, not force. What is the meaning of that? The meaning of that is that if I want to measure how much force is being applied, for example, if I have a cantilever beam, and I apply a force of 10 newtons here. Now this 10 Newton will cause a strain here. So what I do is basically I put a strain gauge. Okay, I put two strain gauges, one there and one here. And then how does the strain gauge work? Strain gauge basically is something like this. There's a very thin wire. Okay, there's a very thin filament of wire like this. And I give a voltage across plus and minus across the terminals of the strain gauge. Now, when there is a strain, what happens is the cross section of this wire, very thin wire, changes. Now, if the cross section changes, if the cross section decreases, then the resistance will increase, right? So less current will flow in that circuit. So essentially, when we are putting a strain gauge here, what is happening is this material can bend like that, and when it bends, what is happening? There is a strain here, and once there is a strain, this element gets strained, and this wire gets strained means its thickness is decreasing, its length is increasing, and because of which the resistance of the wire is increasing. If the resistance increases, less current will flow through it. So I can calibrate this like this, say force versus voltage. So I start off with say 1 Newton, okay, 2 Newton, 3 Newton, 4 Newton, and I see what is the voltage which is flowing through the strain gauge. Okay, and then I plot it, and then I fix a straight line. So if I get an unknown voltage, then I can very easily see what is the corresponding force that is being applied. So if I have to calibrate the strain gauges, load cell as force sensors, they're exactly the same. You have to calibrate them first. Once you calibrate them, it means you're finding a relationship between the voltage generated in the voltage flowing across the current flowing across the strain gauge and the corresponding force which is being applied. So if you put an unknown force, I put a force of say n newtons, okay, or x newtons. So this is my force of x newtons. I go back here, I see what is the current passing through this. I come here, and then I say that this is the force now, which is acting at the tip. So something very, very important to note. Please do think about this very carefully. This is very, very important, that we need to understand that you cannot measure force and position. You cannot measure force or moment directly. Okay, you can measure them indirectly. So what you're measuring is not force, but you're measuring the effect of force. And what is the effect of force? It is strain. So you're basically measuring strain, and then having a calibration to go backwards, that if this is the voltage, then this is the force being applied. Okay. Now, the other important question here is, in a beam like this, in a cantilever beam like this, how many forces can you measure? Okay, so we can have a strain gauge which is placed here and strain gauge which is placed here, which can measure this force. Okay, that's my force N. So that's one force, either this side or this side. That's one force. What about the other one? You can have a strain gauge on this side and on the other side. So you can measure the second force, which is on this side. Okay, so you can measure the other force on that side or this side. So you can measure two forces with one beam element like this. Now we know that there are three forces and three moments. What are they? Fx, Fy, and Fz. Mx, My, and Mz is the other moment. Okay, so there are three forces, three moments, means 6 of them. So if one element can measure only 2, then you need at least 3 to 4 elements. You need at least 4 elements actually, or 4 beams to measure 3 forces and 3 moments. Okay, so the construction of the strain gauge is something like this, where we have 4 beams. So this is the wrist of the robot. Let's say this is my wrist. Okay, so let me draw it here and explain how this works. Is we have so on the wrist of the robot, say if this is my wrist, I'll fix the force torque sensor, which is here, and the end effector is fitted there. Okay, so this is my wrist, and this is the end effector which is fitted here. Okay, so this is this part. Okay, so on one side we have the wrist of the robot which is fitted here, and the end effector is fitted here, so something like this. That's my end effector. Okay, so when the force or the moment acts, it acts on the end effector. So the forces and moments should be acting on the end effector, right? And which is felt by the robot. So the forces and moments are acting on the gripper or the end effector, and they are being transmitted onto the wrist of the robot like this, as is shown here. Okay, so this is my FT sensor. Now on the force torque sensor, you can see that there are 4 beams. And on the 4 beams, we have strain gauges. There is one strain gauge here, here, and there. And my axis notations are given like this. This is my x-axis, this is my y-axis, and that's my z-axis, which is coming outward. Now, in each of this end of the cantilever beams, remember that this is a cantilever beam. One end is fixed, and it's a beam. Okay, so there is one force in this direction, and there is one force in that direction, which can act. So each beam can take 2 forces. So let me draw a 3D view like this. Okay. So each of this, there will be forces here and here, 2 forces each. Okay, so this is the figure which is showing. So on each of them, there is a W1, W2, W3, W4. So these are the forces. So the cut section here, the internal section here is shown there. So W1, W2 up to W8 are the forces which are acting at the end of the strain gauges. So this would be my W1, W2, like that. Okay, this fixed end is the fixed end here. Okay. So each of the end of the beams has two forces, and there are 4 of the beams. So there is 1, 2, 3, 4 here. So there is 4 into 2, which is equal to 8 forces, W1 to W8. Okay. Now, for static equilibrium, we know that sigma F must be equal to 0 and sigma M must be equal to 0 also. So if sigma F is equal to 0 and sigma M equal to 0, so we take one at a time. So Fx, Fy and Fz. So I say the first one is sigma Fx equal to 0, which means that all forces in the x direction are equal to 0. So in the center, if I apply my Fx, Fy and Fz, Mx, My and Mz, I need to find the relation between this and the forces which are acting here. This is my W2 and that is my W1. Okay, so I need to find the relation between the external Fx, Fy, Fz, Mx, My, Mz and the internal forces W1, W2, W3, okay, which are the relation between them. So I start off, so we have 3 force equations, 3 moment equations. Okay, so I say sigma Fx equal to 0, the first one. So all forces in the x direction are 0. That means Fx, the capital Fx, which is my x direction. This is my x direction. Okay, that's my x direction. Okay, so sigma Fx must be equal to, what are the forces in the x direction here? There's one force W, so that's my upward direction, no, it's x. So this one plus that one, W3 plus W7 is equal to W3 plus W7. Okay, so this is my W3. So this is W1, W2, W4, W5, W6, W7, W8. Okay, and so this is my first equation. So I get K13 and K17. These are gains into W3 plus W7. In the y direction, so in the y direction, which is this side, so which are the forces in that direction? So it's very easy to see W1 and W5. W1 and W5 are forces in that direction. So W1 and W5. These are the gains. In the case of moments, what about Fz? In the z direction, we see there is W2, W4, W6 and W8. Okay, so you can refer to this figure and see. In the case of moments, there is a moment about the x-axis, which is Mx. What is causing that? So W4 and W8 are the two forces causing the moment about the x-axis. So there's a W4 and W8. Okay, so these 3 are moments, those 3 are forces. Okay. Now it's interesting to note that this matrix is basically a 6 by 8 matrix. Okay, so it's a non-square matrix. So I can write it in the form F is equal to W into F is equal to K into W. So I can write this as F is equal to K into W, where W is the fingertip, is the forces. So I need to calibrate this. Okay, how do we calibrate? We calibrate by putting small forces in the Fx, Fy, Fz direction, Mx, My, Mz. So put these 4 forces, let's say in the x direction, I apply a force of 1 Newton, then 2 Newton, 3 Newton, 4 Newton. Look at the reactions at W3 and W7. Okay, and then draw the graph. Similarly for Wy, for Fy and Fz, I need to do calibration. Similarly for Mx, My and Mz, I need to calibrate. After I calibrate, I can get these gain values. So K13, K17 are variables or gains. I need to find out what is the value of these gains, and that I can do by calibrating it. And once we calibrate it, then I know what is the relation between. I need to find these values, right? Then what I can do is I can say W is equal to K inverse into F. Okay, but what you see here is that K is a non-square matrix. It is 6 by 8, which means that the generalized solution of this equation is W is equal to K pseudo inverse F plus K hash K minus I into lambda. Okay, so which means that this is in the null space, and this is my null space, which means, and this is not equal to 0. So it means that there is always some error in force measurements, in force moment measurements because of this. Okay, so please note that when you're measuring force because when you're calibrating it, there is always some error because K is a non-square matrix. So you'll never be able to find W exactly. Okay, so this is one issue. The second issue is that if you look at the matrix here for Fz and Mz, Fz and Mz, for Fz there is 4 elements which are responsible for Fz. It's a W2, W4, W6, W8. What does it mean? It basically means that when you're calibrating for Fz, any combination of this 4 of them could give you the same Fz. So it is not unique because this is a non-square matrix. Similarly for Mz, there is a combination of 4 elements here. Okay. Now unlike Fx, Fy, in Fx there are only 2 elements. Okay, so when you're writing this equation, there is only 2 of them. Okay, so Fx is equal to W3 plus W7. So this can be resolved. But the moment there are 4 elements here, now any combination of these 2 elements can give you the same Fz. And that happens because this matrix is a non-square matrix. So Fz, so the other thing to note is that Fz and Mz are caused by a combination of 4 forces. Okay, so no unique solution, no unique solution. Okay, so these two issues will result such that these two issues cause the problem that you never get exact in force torque measurements. There is always going to be some error. So please keep this in mind if you're ever using force torque sensors, that you always tend to get some kind of error in force torque sensors. Okay, and that happens because of this K matrix, which is non-square. Okay, now let's so much for the different sensors that we talked about. We talked about the encoder, then we talked about the potentiometer. The encoders was incremental encoder, then we had absolute encoder, then we talked about proximity sensors, then we talked about from proximity sensors we moved on to talking about force sensors, force torque sensors. Okay, now we'll move on next to actuators. Now actuators, as we say, are energy converters. So they convert normally electrical energy to mechanical energy. Electrical energy to mechanical energy. Okay, and they are used because we talked about. Now here let's just go look at this and then come back again. So here it basically says that actuators can be of different types. You can have electrical actuators which are converting electrical to mechanical. You can have pneumatic actuators which are converting pneumatic, that means air pressure, to mechanical motion. Okay, so this is very common. This is used in the links, motion of the links. This is used in the grippers. So the opening and the closing of grippers, if I draw a robot hand like this, so the opening and the closing of this is controlled by pneumatic air pressure. Okay, so this can be for opening closing of grippers is pneumatic. Hydraulic, where we are converting fluid pressure, normally oil pressure, to mechanical motion. So these are hydraulic actuators. They are basically piston cylinder mechanisms. So in a piston cylinder mechanism, there's a piston and a cylinder, and these are two sides. So when air goes in from this side, it pushes the piston on this side. When the air comes out from here, and air goes in from here, it'll push the piston backwards. Similarly, in hydraulic also, the motion is exactly that way. The fourth is what we call advanced actuators. They can be called as, they are basically ultrasonic motors, artificial muscles, molecular motors. Now, there is something called the size effect. Now, the size effect means that you can shrink to a particular size, but not beyond that. So if you want to make a very small robot, how small is small? We can make a very small robot, let's say 10 millimeter robot, or even smaller than that, say 2 millimeter robot. Now, if you put a DC motor and put a very small DC motor, say 1 millimeter DC motor, it's not going to work, because you know that the magnets which are very small will not have that kind of magnetic flux or magnetic strength, because of which it will not be able to produce enough torque to move the links. So the size effect basically says that you can shrink something like a normal robot or a normal NC machine, CNC machine, but to a particular size. Beyond that, it doesn't work. Why? Because these actuators like DC motors, AC motors, they don't work beyond a particular scale. Okay, and that is called the size effect. So if you want to go to a small size, let's say 10 millimeter or even smaller, 1 millimeter, 2 millimeter size, then your actuator cannot be electrical, pneumatic, hydraulic, because those small actuators will not give you enough power. So in that case, you need to use other kind of actuators. Okay, and those actuators are basically called advanced actuators. For example, ultrasonic motors, artificial muscles, molecular motors, which work at very small scales, and they're independent of the size effect. Okay, as we go along, we'll see what are they and how are they applied. Okay, now let's go back. So there is a mapping which goes on between the actuator space, joint space, and the end effector space. This is something we talked about in the Jacobian. So the actuator space is basically voltage, the joint space is degrees, and the end effector space is Cartesian space x and y. Okay, and there's a mapping, and what relates this to this is the Jacobian. This is something we talked about, x dot is equal to j into theta dot. Okay, now we are saying that, and this mapping can be very funny, that in case of j being non-square, so it can be m into n. In that case, there is also a null space. Okay, so some of the velocities that you're going to give to the actuator can go to the joint space, and from the joint space it can go nowhere. It can go into the null space. Okay, so it's very important to understand how the mapping of j is and how there is the transformation that takes place between joint space to end effector space. Okay, so let's start off by looking at the various electrical actuators, then we'll look at pneumatic, hydraulic, and advanced actuators. Now, the other important question here that comes up is, which actuator are you going to use when? Okay, for example, you're designing a robot. So I'm making a robot. Let's go back here. So I'm going to make a robot. Let's say I have a robot here, a robot of this type. So this robot is rotating about this axis. Then there is a shoulder axis here. Okay, there is a shoulder axis, and there is one more axis here, let's say, and the end effector is here. Okay, so this is my robot, and I want to decide which actuator to put where. So the first thing that I need to do when deciding motor torque is I need to do the dynamics, and from the dynamics I write, so our dynamic equation becomes m theta theta double dot plus v theta theta dot plus c theta is equal to tau. Okay, so when this robot is moving around in space, in the workspace, it moves around in different locations. It can pick up a weight, it can pick up a mass, and then drop it also. Okay, so maybe it picks this up and drops it, or does some particular task. So to move around in a particular trajectory, we can compute what is the theta, theta dot, and theta double dot by using trajectory planning. So from trajectory planning, I can put it in here, and I get what is my joint torques. Okay, now depending on the joint torques, I have to decide my actuator now. Okay. Now normally, the base link of the robot, this is the base link of the robot, will carry the maximum load. Okay, why is the base link carrying the maximum load, or this link is carrying, depending on what is the structure. Okay, so in this particular case, for example, when the arm is stretched out maximum like this, okay, that is the one that is carrying the maximum load, because your mg is coming here, and this is L1 and L2. So your full load is mg L1 plus L2. Okay, that's the full load which is coming on this shoulder joint. Okay, now the shoulder joint is normally carrying the maximum load plus the waist joint, the base joint. Okay, carries the maximum load for the robot. So very often the base joints, so the base joints are hydraulic. The in-between joints are electrical, and the last joint, the gripper, is pneumatic. Okay, so out of all these actuators, basically the electrical one, the weakest one is the pneumatic one. The strongest one is the hydraulic actuator. So hydraulic actuators are the strongest actuators, okay, because they work on fluid pressure. The weakest is the pneumatic actuators, because they work on air pressure. And in between pneumatic and hydraulic is electrical actuators. Okay, so in a robot, normally you can have the base to be actuated by hydraulic, So industrial manipulators, when you look at the industries which carry, where the industries where robots carry very heavy loads. What is heavy load? Say 100 kg, 100 kg or 200 kg. Such robots which carry such heavy loads, they are normally hydraulic actuators. Okay, the base joints of these robots are actuated by hydraulic energy. In between, it is electrical. So in between, it is electrical. And the last is the gripper, is pneumatic. Okay, why is the gripper pneumatic? Because first of all, it is the softest or the weakest. So if the gripper is actuated by pneumatic, suppose the robot is moving and it hits something, then immediately the gripper will open and the part will fall off. Okay, because pneumatic actuators are back drivable. So if you press it in this direction, for example, we have a robot like this, and it is holding the end effector. There is a part and it hits something here. What will happen? The gripper can immediately open, or the shock of getting hit can be transmitted onto the pneumatic actuator. It can go backwards, or it is back drivable, whereas other actuators are not back drivable. Okay, and because of this, then grippers in robots are very often pneumatic because they are just open and close, whereas the in-between joints are electrical. So for example, here I talked about the independent joint control, so motor, encoder, gear. Suppose the robot hits, what will happen? The force will come here, and the force will be transmitted onto a torque at every joint. Now, because there is a gearbox here, it is not back drivable, so the joint will not rotate backwards. So what happens is the gearbox will break, or the link will break. Okay, so whenever you have a high gear ratio, what happens is that if it hits something, the links gets damaged, and the links tend to break. Now, if the links break, then obviously it doesn't help, right? So in case of the gripper, what is done is we basically make it using pneumatic actuators. Also, very recently there is talk of safe robots. We talk about safe robots. We also talk of cobots, collaborative robots. Now, cobots and safe robots are such that they have to be safe. So when you say safe, what does it mean? It means that if you hit something, either you hit a human or you hit a wall or a table, the robot should not get damaged. So, and that requirement is that the link should be soft, maybe it can be made of flexible material, or the joint should be able to go backwards. Okay, so if you want the joint to go backwards, you cannot put a very high gear ratio because of the high friction. You cannot rotate the gearbox in the reverse direction. It goes only in one direction. Okay, so in such cases, there is a lot of challenges or a lot of new robots which are being developed, which are safe in terms of design of actuators, in terms of design of gearboxes, in terms of controller stiffness that will come to when we come to control systems. Okay, so please note that there are different kind of actuators, and depending on what how much energy you want, you can choose a particular kind of actuator. We'll start off with electrical motors, then move to pneumatic, hydraulic, and then advanced actuators. Now, electrical motors can be stepper motors, DC motors, or servo motors. The working of a stepper motor is very, very simple. Now, the stepper motor consists of a rotor. So this is my rotor. This is my rotor. And this is my stator. Okay. The rotor has teeth, and which has windings. You can see that these are teeth on the rotor. So these are the teeth, and there are windings. So these are windings on the teeth. Okay. How does it work? The rotor has teeth. You can see that these are the teeth on the rotor. Now the stator the stator also has teeth, which you can see, or projections, and there are windings on the stator. Okay, so this is my rotor, and those are the stator, and the stator also has teeth, and the rotor also has teeth. Now, how does it work? Now, this is normally can be made up of a permanent magnet, or it can be made of a ferromagnetic material. Okay, so if it's a permanent magnet, then automatically north-south poles are there. Okay, now how does it work? Is suppose I actuate this pole, I energize. So if you energize, that means you give a voltage to this pole. What would happen is I'm giving a voltage to this coil. Now a current is going to pass through that, so it is going to induce a magnetism here, a magnetic field. Now this one already has a north and south, so this induced magnetic, so this is north and south. What will happen is this north will be attracted to that south. Okay, so what happens is when I energize pole B, or this teeth B, what would happen is it will create a magnetic field which has this has a north south, this will be a south north, and this will attract the teeth there, and this will align against that. Then what I do is I energize this one. So what will happen? This will move this side. Then I energize this one, this will move this side. So energize in sequence like B, C, D, A, and the rotor is going to go clockwise. Okay, this is a figure which shows that I energize B, then so what happens? C aligns against this, then energize C. Okay, what happens? 5 energizes here, this one moves this side. Then I energize D, this goes here, and I energize A, which goes here. Okay, so if I energize B, C, then D, then A, so it goes in the clockwise direction. If I go in the reverse direction, then it becomes counterclockwise. So these are basically called stepper motors, and stepper motors can be operated in micro stepping mode also. If I energize 2 poles together, if I energize this one and this one together, then this teeth will go somewhere in between. So let me go to the previous figure. Suppose I energize this pole and this one together, then what will happen? This will come and stop somewhere in between, because it will have equal attraction from this side and that side. If I give a higher volt, if I have 2 voltage V1, V2, so depending on the ratio V1 by V2, depending on this ratio, I can control the position of the tooth there. If V1 by V2 is greater than 1, so if V1 is greater than V2, V1 is greater than V2, this teeth will go more that side. So this is basically called micro stepping. So in micro stepping mode, you can place the tooth somewhere in between here also by controlling the voltage of 2 coils. Okay, you can also have mega torque motors, which are like this. Okay, and we can also have linear stepper motors. So this is a linear stepper motor. Working principle is exactly the same. We are energizing. So this is my the magnets. So first I energize magnet 1. So this tooth is attracted there. Okay, then I energize magnet 4. Okay, so this tooth is attracted here. So this is moved this side. Okay, then I energize 2. Then I energize 3. So this is every step, it is going in steps in this direction. And these are linear stepper motors. So you can have linear stepper motors, and we can also have rotating stepper motors. This can also be operated in micro stepping mode. So we talked about stepper motors today. The disadvantage of stepper motors is that because they are made of permanent magnets or ferromagnetic material, they are very heavy. Although the torques of these motors are very heavy, are very high, and their cost is very low. Okay, you can get a good stepper motors for about 500 or 600 rupees, but they are very, very heavy, so they cannot put on the outward links of the robot. Okay, and hence we don't use them for robotics applications normally. We can use them on the base of the robot, but not in the forward links, because they are very, very heavy, and that causes very high torque requirements on the robot. So we'll stop here today, and we'll continue in the next class. Thank you.